When a shark's tooth tears into the Elasmosaurus, the periosteum, that thin membrane covering the bone, gets ripped open. The blood vessels inside it rupture, and blood spills out. It doesn't just flood the surrounding soft tissue, it actually seeps into the crack in the bone itself, working its way into the tiny gaps between the hydroxyapatite crystals that make up the hard bone structure. Now, in warm seawater around 25 degrees Celsius, blood thins out faster than it would on land. But clotting still happens. Platelets rush in, a fibrin mesh starts to form, and a blood clot gradually builds up right inside the wound. Meanwhile, the stem cells in that torn periosteum have been quietly dividing, and now there are enough of them. They start differentiating into osteoblasts, the cells that actually build bone. These osteoblasts travel into the crack along newly formed blood vessels that grow in from the edges of the wound inward. The osteoblasts begin secreting collagen, not hard bone yet, just a soft, flexible protein mesh that fills in the gap first. This collagen network then acts as a scaffold, giving minerals a surface to attach to, mainly calcium phosphate in the form of hydroxyapatite crystals, which is what gives bone its hardness. This mineralization process moves from the outer edges toward the center of the crack, kind of like two riverbanks slowly closing in on each other from both sides. In the early stages, this forms what's called a cartilaginous callus, tissue that's somewhere between soft and hard, more flexible than real bone, but strong enough to bridge the two sides of the fracture back together. 80 million years later, paleontologists lift a fragment of fossil under a microscope, and they realize this creature was once bitten, healed itself, and kept on living. These stories exist inside the bone like fragments of ancient memory.